Assalamualaikum warahmatullahi wabarakatuh. Distinguished guests and esteemed members of the scientific community, it is with great pleasure that I stand before you today to present my research findings on a subject that holds immense significance in the realms of machining and energy efficiency. First and foremost, allow me to introduce myself. My name is Muhammad Nasrin bin Dzulkiffli. The culmination of my effort has led to a comprehensive study that explores the remarkable potential of hybrid nanolubricant in significantly reducing power consumption during the turning process, specifically focusing on the challenging material known as Inconel 718. My research aimed to evaluate the impact of hybrid nanolubricant on cutting power consumption, specifically in the context of Inconel 718 turning under MQL conditions. Firstly, I would like to discuss the fascinating world of machining and the challenge posed by a remarkable material called Inconel. Inconel, a category of nickel-based superalloy, is renowned for its corrosion resistant, lightweight properties, and ability to withstand high temperature. Consequently, it finds application in critical sectors such as nuclear, automotive, aerospace, and marine industry. However, machining Inconel presents significant difficulty due to its strength. The friction between the cutting tool and the workpiece generates heat, resulting in increased energy consumption, altered cutting force, compromised surface quality, and tool wear. To combat this issue, lubricants play a vital role in the machining process. Lubricants serve multiple functions, including dissipating excess heat, providing lubrication at the tool workpiece interface, facilitating chip removal, preventing erosion, and improving tool life and workpiece finishing. However, conventional lubrication methods have their challenges. Increased fluid usage leads to high costs, especially when using the flooding technique. Moreover, conventional lubricant can pose health risks to machine operator and contribute to environmental pollution. In recent years, there has been growing awareness of environmental and health concerns, leading to the adoption of the minimum quantity lubrication (MQL) technique. MQL targets the cutting zone with a minimal volume of cutting fluid, addressing both environmental and health-related issues while potentially reducing production costs. However, MQL may compromise cutting fluid performance due to its inferior thermal conductivity. To enhance lubrication efficiency, researchers have explored the use of nanolubricant in conjunction with the MQL technique. Nanolubricant, which consists of a nanoparticle dispersed in a base fluid, offers superior heat transfer capability and improved tribological characteristics. They act as efficient cooling and lubrication medium during machining process. The small size of nanoparticles enable them to form a thin, protective tribofilm that reduces friction and wear by preventing direct contact between cutting tools and materials. Despite these promising advantages, the widespread industrial application of nanolubricants face economic and technological limitations, such as long-term stability, increased pumping capacity, and pressure reduction. To overcome this challenge, researchers have proposed hybrid nanolubricants, which are a combination of two or more distinct types of nanoparticles in base fluid. Hybrid nanolubricant show improved thermal conductivity compared to nanolubricant containing a single type of nanoparticle due to the synergistic effect. However, hybrid nanolubricants are still in the research phase, with limited studies conducted in the turning operation. Therefore, the focus of this study is to investigate the impact of hybrid nanolubricant on cutting energy during Inconel turning under the MQL approach. The utilization of lubricant, specifically nanolubricant in the machining of Inconel, is crucial for overcoming the challenge posed by this exceptional material. Hybrid nanolubricant with their improved thermal conductivity show great promise for enhancing machining efficiency while addressing environmental and health concerns. The ongoing research in this field will undoubtedly contribute to the advancement and commercialization of hybrid nanolubricant, revolutionizing the way we approach machining process in various industries. Next, for the methodology of the research, this experiment is divided into three distinct phases. In phase 1, the researchers have prepared a hybrid nanolubricant and gathered all the necessary requirements for the experiment. The selection of nanoparticle for the hybrid mixture was based on previous finding. The hybrid mixture compromised a 1:1 ratio of aluminum oxide and zinc oxide nanoparticle, which is accounting for 0.3 weight ratio of the mixture. These nanoparticles were dispersed in a semi-synthetic cutting fluid, utilization sulfate oil as the base oil. To stabilize the mixture and prevent agglomeration, SDBS was incorporated. All cutting processes were carried out under MQL condition, which involved the use of a CNC turning machine, Chevalier FCL 608, equipped with a specialized insert and MQL applicator featuring two nozzles. The experiment will perform on Inconel 718 with a workpiece dimension of 100 mm length and 50 mm diameter. The research design involved maintaining a constant feed rate and depth of cut while varying the lubrication and cutting speed parameter. To measure and record data during the machining process, the researcher employed a picocurrent data logger or picolog. This instrument recorded the electrical current throughout the experiment and was connected to a laptop via USB interface and the machining through a three-phase wire. Moving on to phase 2 and phase 3, the researcher conducted the actual experiment and analyzed the result. The cutting condition employed a tool wear of VB 0.3 mm. The experiment focused on evaluating the performance of the hybrid nanolubricant mixture in terms of tool wear and cutting condition. The collected data was analyzed and the power consumption during the cutting process was evaluated. Lastly, this research study presents an innovative approach to enhancing cutting process through the utilization of hybrid nanolubricant. By conducting experiment, analyzing results, and assessing power consumption, the research aims to achieve their objective and contribute valuable insight to the field of machining and lubrication. Continuing our discussion, let's delve into the result obtained from this research study, specifically focusing on the power consumption during the machining process. As you can see, figure 1, our experiment has provided valuable insight with the average reading for various parameters as shown in table 1. First, let's discuss the finding regarding cutting power. We discovered that the highest average cutting power, reaching 9.66 kW, was achieved through dry machining at a speed of 100 meter per minute. On the other hand, the lowest average cutting power, measuring 6.11 kW, was observed when using a hybrid nanolubricant at speed 25 meter per minute. Interestingly, these results support the theoretical basis presented in our reference, which suggests that hybrid lubricant machining consumes less power compared to single nanolubricant based machining. This is mainly due to the superior heat transfer capability of hybrid lubrication and its ability to significantly reduce friction between the tool and the workpiece. Now, let's delve into the reason behind this finding. The peak average power consumption of 9.66 kW was observed during dry machining at the highest speed of the 100 meter per minute. As the machining speed increased, we observe a corresponding acceleration in flank wear progression on the cutting tool. In simple terms, the tool wear out more rapidly with higher speed. This effect is further exacerbated by the dry machining method, which lead to faster tool wear and increased friction between the workpiece surface and the tool tip. Consequently, the power required for the cutting process rise. During dry machining, chemical reaction also occur due to significant heat generated by the shearing of the workpiece chip. This reaction gradually diminishes the coating on the tool tip, eventually leading to its complete loss. Lastly, the lowest average power consumption of 6.11 kW was recorded during the operation of the hybrid nanolubricant at the slowest speed of 25 meter per minute. Continuing our discussion on the effect of various lubricating conditions on total cutting time. In this study, the researchers investigate the impact of different lubrication methods on the efficiency and power consumption during cutting process. The finding revealed some interesting observations. Let's begin with figure 2, which illustrates the total cutting time under different conditions. It was observed that under dry condition, the cutting time was the shortest at a speed of 25 meter per minute, requiring only 2.5 minutes. In comparison, the single and hybrid nanolubricant condition took 4.6 and 6.3 minutes, respectively. Interestingly, chipping occurs more rapidly under dry condition, leading to increased power consumption. However, the power consumption was the lowest with the hybrid nanolubricant, indicating that the depression of zinc oxide nanoparticle into the cutting tool helped protect the tool exposed region. Let's move into the figure 3. We find that at speed of 50 meter per minute, the total cutting time under dry condition remains shorter at 3.5 minutes compared to the scenario involving nanolubricant. The difference in cutting time between the single and hybrid nanolubricant was not significant, with the single nanolubricant requiring 4.1 minutes and the hybrid nanolubricant taking 4.3 minutes. However, the power consumption was considerably lower with the hybrid system, and the total cutting time was longer compared to the single nanolubricant. This graph clearly demonstrates the advantage of employing a hybrid nanolubricant using the MQL technique. Next, figure 4 presents the result at a speed of 100 meter per minute, where the hybrid nanolubricant show greater efficiency and reduced power consumption compared to the single nanolubricant and dry condition. The tool longevity was also improved with the hybrid nanolubricant, with a total cutting time of 2.35 minutes compared to 2.183 minutes under dry condition and 2.25 minutes with a single nanolubricant until the tool reached the end of its life, even in case where the tool was already worn. The hybrid nanolubricant decreased the machine power consumption. Research support this finding, suggesting that the combination of two or more nanoparticles form a triple film that reduce frictional power loss and provide anti-wear and anti-scuffing properties. In conclusion, the use of hybrid nanolubricant consisting of aluminum oxide and zinc oxide nanoparticle in a ratio of 1:1 has demonstrated significant benefit in machining operation across different cutting speed. This hybrid nanolubricant has shown lower average power consumption and extend to life, resulting in improved machining power consumption performance. Compared to the dry machining, the hybrid nanolubricant has achieved a remarkable 53% reduction in power consumption at a speed of 25 meter per minute, a 29% reduction at 50 meter per minute, and a 39% reduction at 100 meter per minute. When compared to the single nanolubricant, the hybrid nanolubricant has yielded a 13% better power reduction at 25 meter per minute, a 13.1% better reduction at 50 meter per minute, and a 7% better reduction at 100 meter per minute. While the comparison with a single nanolubricant may not show a highly significant reduction in power consumption, the overall result fulfills the objective of this research. In summary, the suspension of aluminum oxide and zinc oxide nanoparticle in synthetic oil forming a hybrid nanolubricant has proven to enhance machining process performance. It achieves this by reducing the coefficient of friction and power consumption compared to a conventional single nanolubricant system. These findings have important implications for the industry, as they offer promising solutions for improving efficiency and reducing energy consumption in machining process. For future recommendation, the utilization of the technology method is suggested to identify the optimum parameter for the hybrid nanolubricant system. By further optimizing the lubrication condition, even greater improvement in power consumption and machining performance can be achieved. Thank you for your attention throughout this presentation. If you have any further questions, I will be happy to address them.